now you're going on a fantastic trip, and the person who's going to take you on that trip is Harvey from the Perth Observatory. Enjoy.
Thank you very much, and what an absolute privilege it is to be here in front of this audience today. We've had some fantastic academic papers here, the brilliance of professorial minds, and I can agree with what's been said, particularly by Professor Blair, because when we have students come to Perth Observatory, it's the modern things that they read and see and hear about black holes that really are of interest to them. Newton, a name from the past, an important name from the past, but it's the modern world that we need to introduce our children to. And yes, I want to take you on a journey today. Now, in the recent past, if you had a lot of money, you could have joined Richard and flown, and perhaps Jeff's rocket would have been a good way to go as well. But think about this, if I can say it to you. Leaving Earth and going to the edge of space is a little bit like leaving Perth here on a flight to the South Pole, stopping at Jandakot and coming back. So today I want to take you a lot further, perhaps as far as your imagination can be. So in this rocket, and please sir, madam, no need for safety belts in this rocket ship. You're okay. Yes, you can hang on to him as you are. And there's plenty of windows in this rocket. As you can see, we're looking out the back window at the moment because we've already taken off. We're already kilometres above the State Library in which we sit. And as the rocket flies higher, you can see Perth, the Indian Ocean to the east or the left, and up we go. The bottom corner of our continent, you can see the two capes here, and it must be summertime because it's all brown, and there's a bushfire burning, and likewise the smoke is streaming to the west. What would be the first thing that we would see in our journey? It's probably this, the International Space Station. It's almost all solar panel, isn't it? So if you compare it to an American football field, it's fairly big. But as I say, mostly solar panel. As we fly higher, everyone's still comfortable, I hope? No seasickness, no rocket ship sickness? Good, just checking. The next thing we would see is our friend, the Hubble Space Telescope. That's been mentioned a couple of times already today. Now, of course, I noticed in Professor Blair's talk that all of his esoteric arguments he didn't need to support with any equations or whatever like that. And thankfully there are none in my presentation either. But the clever mathematicians among you, and I'm sure there's some out there, will be able to quickly do some back-of-the-hand calculations with the two curvatures of the Earth here and decide which of those two objects is the higher in the scheme of things. Yeah, you don't have to tell me. Right, on and on we go. Our planet is surrounded by satellites, artificial satellites. They form three spheres, the LEOs, the MEOs, and the next lot. The low Earth orbit ones are only about 800 or so kilometres up, so a couple of 100 kilometres above the space station and the telescope. The next lot, the medium Earth orbits, are a little bit further away. They're the ones that give us our GPS satellite information, etc. And the GEOs, the furthest ones out, these are the geostationary satellites. there's lots of them there, and they provide our communication, about 600 or more of them, at 36,000 kilometres above. So already we've beaten the billionaires, haven't we? We're a long way out. Australia has its own fleet of GEO satellites to provide us with coverage. They're mostly owned by Optus, I believe. Not that my phone runs on Optus, but still. No advertising here. So this is just a graphic of how those satellites at that altitude stay in sync with a particular place on the planet, so that they can provide that communication directly to that location. As I say, Australia has I think we've got 2 active and 2 spare, and maybe an extra one or so or 2. Now I'm going to have to pause here and go back to the flight controls of this rocket, which are tucked over here somewhere. So if I'm silent for a moment, it's because I'm negotiating our way through these maze of satellites. There's 14,000 of them at least up there. Yes, it's surprising, isn't it? And some of them have odd orbits, as you can see. So yes, I think I've dodged the most of those, so relax everybody, we'll fly on. Our natural satellite, the Moon. The Moon's been discussed a little bit in the previous presentations. This GIF provides you with 1 month of the Moon's movement, and you'll notice that apart from rotating on its axis, it's also wobbling a little bit like this. It's the correct term. Wobble's not a scientific term, I realise. So the correct term is librate. So the Moon librates such that in a month we can see about 60% of the surface that faces towards the Earth. 60% of it. Unlike our friends, there is no dark side to the Moon, in spite of what Black Sabbath might have said. Sorry, Pink Floyd. My mistake. In spite of Pink Floyd, there's a far side to the Moon. The Moon happens to be tidally locked to the Earth, so that as the Moon rotates once on its axis, it also orbits the planet Earth once in the same time frame, and that causes the one face to face us. This is a topologically coloured map of the far side, and you can see that it's far more cratered than the near side, the one that faces us. And that makes sense as well, because during what's called the heavy bombardment period, lots of incoming meteorites hit the far side of the Moon rather than hitting the near side. Just to make it clear, when I say the Moon orbits the Earth, it's a two-body situation where the centre of the orbit is not the centre of the Earth. It's the centre of mass of the two objects. It just so happens that the centre of mass is inside the Earth by about 1,000 kilometres or so below the surface. So what is in effect happening is, as you see here, here's the centre of mass with the red cross, and the Moon is moving in this way, but also the planet is, if you were viewing it from a distance, you would see the planet move back and forth a little bit. And indeed, this is true of the entire solar system. So the Sun also, from a very distant view, would appear to move back and forth as the planets gang up on one side or not. The difference being that the centre of mass of the entire solar system moves from being slightly inside the surface of the Sun to slightly outside. Let's move on. I've told you all about that. So we'll deviate and have a quick look at the Sun, our Sun. You can see by the position of these sunspots that they're the same ones, so that you can tell that the Sun is rotating. It's doing about one rotation on its axis about every 25 days or so. But of course the sun is not a solid body, so that's really at the equator. The poles would be slightly different. We heard about the probes going to Mars, but we've recently sent a probe to the sun, the Parker Solar Probe. It's flying in this elongated orbit, such that it comes within about, someone will correct me if I'm wrong, I think it's about 7 to 9 million kilometres from the surface of the sun. That's got to be pretty warm, hasn't it? It's probably got this long elliptical orbit to cool down a little bit after those close approaches. So it's got lots of instruments on board, hidden behind this heat shield, that will tell us a lot more about the sun compared to what we know now. The view of the sun, if you would look at it with your own eyes, which of course would be dangerous, is this side of the sun here with a sunspot on it. This is called the photosphere of the sun. On the other side is called the chromosphere of the sun, and that shows us the active surface of the sun. So even through the solar telescopes that we have at Perth Observatory, we can show you a pretty reasonable view of our sun. Of course, don't come on a cloudy day though. As happens often enough. With much more powerful solar telescopes, you can get fantastic images of the sun, including of these massive coronal mass ejections here. And remembering that the sun is 1.3 million kilometres in diameter, our Earth would be, not much bigger than a small dot like this. So it just shows you how big and powerful these ejections are. Of course, this particular one would be good from our point of view, because if this was taken from Earth or near enough, then you need to have one of these ejections coming from the centre of the sun or thereabouts, because it's those ones which are projecting charged particles towards the Earth. Here's also a solar photograph taken by SOHO, the big solar observatory. You can see the diameter of the sun here and the mask covering that sun, our sun, so that you can see how far out into space, remember 1.3 million kilometres that distance, how far out into space that material is ejected. And of course, if it comes directly towards Earth, it would do a fair bit of damage to our, lots of things. But thankfully the Earth has quite a powerful magnetic field, and therefore the charged particles coming from the sun are directed or deviated towards the poles, where you get to see these spectacular lights in the sky, the aurora borealis in the north and australis in the south. I'm sure some people in the audience have seen these for real. Yes? Good. It's often described as a bucket list item. Red and even green can be spectacular, although I'm told that it's probably easier to photograph them to see them sometimes. It is. That's generally true. There you go. Now, Professor Blair did talk about Einstein and the way in which his theories were proved, and I just wanted to touch on, and as our rocket now, we've departed the sun and we're heading outwards now. So this is actually Mercury, and one of the predictions of, or one of the problems by Newtonian mechanics was that the precession of the perihelion, so the perihelion of a planet is its closest approach to the sun, and that position varies over time. And the calculations of the perihelion of Mercury didn't agree with observation. Those calculations initially done by Newtonian mechanics. So when those calculations were redone using Einsteinian mechanics, for want of a better term, then there was a much better agreement with the observations. So that was one of the first proofs, if you like, of Einstein's theory. So a quick a quick lesson there on the perihelion. Now, I'm certainly not going to talk about Mars today. We have had expert presentations on Mars, so I'm going to skip over Mars, so to speak. It's always good, though, on a really good viewing night at Perth Observatory, all the factors in our favour, we can actually show you the polar caps at Mars. How good is that? But there is something that I wanted to mention, because I was fully expecting Professor Benedict's to be here. And indeed, as we leave Mars, we're going to fly through the asteroid belt. And I was going to ask the professor if she would allow me, or us, in our rocket, to deviate to the asteroid in the asteroid belt that's named after her. But she's unfortunately not here, so I can't sort of do that, except in absentia. It's actually asteroid 6579, and now named after Professor Benedict. So there's the asteroid belt, the rocky inner planets, the asteroid belt, and we zoom out past those to the gas giants, Jupiter, with the famous storm found or first observed by Galileo around about 1610 when he pointed that tiny 40mm telescope towards the big planet. Big planet, but spins very quickly compared to Earth. And the Galilean moons, Io, Callisto, Ganymede, and Europa, but not in that order. This is a montage, of course, to put it in the context of the big red spot. Saturn, the ringed planet, always a favourite with observers at Perth Observatory, I might add. Also spins very quickly. And once again, under ideal viewing conditions, we can show you the Cassini division, this gap in the ring system here. When you observe the ring system in fine detail, you see that it's effectively striated right across the rings. And one of the reasons for that is that embedded in the ring system are various moons. Saturn's got about 70 odd moons. I think they keep finding more all of the time, so I'm never sure which number to quote, but 70 odd. And some of them are embedded in the ring system, and because of the gravitational effect of that, they push and pull the material in the ring system to stratify it or line it up according to its mass. And that's why you get these pretty fine divisions that you can see all the way. But time and tide, and the rocket's burning fuel, so I better push on. We're out to the ice giants now, which reminds me, two planets in our solar system spin in the opposite direction to the rest. The ice giants, I've got to be very careful here because I'm used to talking to school children at Perth Observatory, and of course, when I do so, I pronounce it as Uranus, which immediately confuses them because they're used to hearing it pronounced differently and accompanying that pronunciation with a nice twitter of laughter. And poor old Pluto. Poor old Pluto. Oh. Will we hear the end of it? Unfortunately, there's only three things that define a planet: orbiting a sun, a star, pulling itself into a spherical shape via its own gravity, and the third one, the one that Pluto failed to achieve, and that is sweeping its orbit clear of similar-sized bodies. So all of the other planets, the main planets, have done that, but out where Pluto is, there's lots of not dissimilar-sized objects. So in that case, the people with the power in these things decided that Pluto had to be downrated. Not the first object to be downrated, I might add. In 1801, when the observatory at Palermo in Sicily found the minor planet Ceres, it was called a planet. But of course, Ceres, being very small, was quickly downrated to less than a planet. What else shall we see as we're heading out past our solar system? We might take a glimpse of our friend Halley's Comet. I'm sure we saw the sort of non-event of when it was here before, and I'm guessing most of us aren't going to see it again. There might be some young ones in the audience who are, but I'm sure most of us won't, unfortunately. It's a very elongated orbit, as you can see here, going way out past the edge of the solar system and looping back in every 76 years or so. So, goodbye, Halley's Comet. We've sent one of our probes out there. This is the New Horizons probe. There's not much to tell you about the scale of it there, but it's about the size of a grand piano, thereabouts. Lots of instruments to study the outer solar system. You can see, unlike the communication dishes on the space station or whatever, because it's so far away, it has a big dish to communicate back to Earth. And you'll also notice it has no solar panels. Bit far from the sun out there. It's out past the Kuiper belt, so the Kuiper belt is like the asteroid belt, but made up of icy particles, not water ice necessarily, compared to the rocky particles in the asteroid belt. And then we reach these two distant probes. We sent those into space way back in the 70s. And they are now a long way from us. Notice once again they have big dishes to talk with us, no solar panels. They're powered by what are called RTGs, radioactive thermal generators. So these use, I think it's one of the plutonium isotopes to generate power for them. And they're heading off well beyond our solar system now in different directions. This is a diagram, not to scale, of course, but they're heading out along with their colleagues to explore the universe, just like we are. In fact, we've overtaken them. It's taken them 40 odd years to get there. We've done it in 30 minutes or less. And comfortably too. So now we're outside the solar system now. We're into interstellar space. And the first stars that we would pass by would be our good friends, the pointers over here, and the Southern Cross. This is the closest star to us, apart from our own sun. This is Alpha Centauri. It's actually a triple star system, Alpha Centauri A and B, which are both very similar sizes to our sun. And then they orbit each other, and then around the outside of them there is Proxima Centauri, which is a faint red dwarf, not usually visible. And of course, they've pointed to the Southern Cross for a long period of time. And because the Southern Cross is circumpolar and therefore visible all through the day and night from our latitude here in Perth at South 32, then we get to see it on our flag, and the New Zealanders get to see it on their flag, although they're a little bit, their eyesight's not so good, so they don't put Epsilon cruises on their flag. They're good at rugby, but got to give them that. You'll notice this dark patch here. This is, in Western astronomy, this is called the coal sack, and Aboriginal astronomy is a very important topic that is just coming to the forefront here in Perth with Perth Observatory. And this coal sack is actually the head of the emu in Aboriginal astronomy. So if you look at it a bit like that, you can see the Southern Cross here, the pointers here, and the coal sack is the head of the emu, which is a large imagined structure in the night sky, following the arc of the Milky Way. There are many, many spectacular pictures of items in the night sky. Astronomy Picture of the Day by NASA, they are fantastic. All beautiful colour, all nicely posed almost. I'm showing you a picture of the largest human eye visible nebula in the night sky. This is Orion's nebula in the constellation Orion. I'm just showing you a simple black and white picture for a reason. It's an image like this you can see through our telescopes at Perth Observatory. Our eyes aren't big enough and the telescopes aren't big enough to show you colour. We don't have a Hubble parked in the back blocks of Perth Observatory, unfortunately. This is where stars are born. This cloud of gas is some 30 light years across. 30 light years across. Light takes 5.5 hours to get to Pluto. So call it an 11-hour diameter. That's the diameter of the solar system. So the diameter of this cloud of gas, 5.5 into 365 times, carry the one. That cloud of gas is 800 times bigger than our solar system. 800 times bigger. You can see it as a fuzzy spot in the sword of Orion with the naked eye, and you can see it very well with binoculars or a telescope. People often ask, how does a cloud of gas in interstellar space start to collapse into a star? Wouldn't a cloud of gas, as it starts to clump together, wouldn't the pressure equally cause it to dissipate again? What's the mechanism there? Well, I had the great good fortune to find in my father's library a book dated 1931, and it's by Sir James Jeans, and he's got a whole string of letters after his name, like our earlier presenters. He's more a mathematician than an astronomer, and it was James Jeans who mathematically showed how a huge nebula of cold, remember how cold this gas would be, close to absolute zero, how a cloud of gas could begin to condense to form, ultimately to form a star. It's an interesting story, but too long for this lecture, I think. But that's the Orion Nebula. Right next to Beta Crucis in the Southern Cross, we have this beautiful open cluster. Clusters in astronomical terms are usually either open clusters or globular clusters. This is an open cluster, so a group of young stars, stars that have only recently formed, but the remaining nebula has been blown away by the light pressure. Remember Professor Blair's mentioned the momentum of light. Light has a pressure, it can push things away. Well, indeed, it has pushed away the remaining nebulosity around the open cluster and left this brilliant capital A type of asterism of stars. Quite visible with a good set of binoculars right beside Beta Crucis in the Southern Cross. Our galaxy, and we're now flying through our galaxy, is a huge disk of stars, 100,000 light years across. We live about 28,000 light years out from the centre, and many of the open clusters are born from star-forming areas within the galaxy. But globular clusters are found in the halo of the galaxy, above and below the plane. This is the opposite of an open cluster. They are huge agglomerations, spherical agglomerations of stars that contain as many as 2 million or more stars. Our Milky Way galaxy has about 150 globulars sitting above and below the plane. As you can see, they are phenomenally dense with stars. It's one area of astronomy that is thoroughly researched because not everyone understands the mechanism that forms globulars. This is M22, one of the largest in our galaxy. We moved from the solar system to interstellar space. Now we're moving into intergalactic space, the space between the galaxies. So our galaxy, obviously it's not a picture of it because we couldn't do that, could we? We haven't sent a probe that far yet. It's an image of our galaxy, imagined, and our two companion galaxies, the Magellanic Clouds. First observed and named by the Portuguese navigator Ferdinand Magellan in 1535 or thereabouts. They are small galaxies and they are already under the gravitational, I heard that word earlier today, didn't I? Under the gravitational influence of our galaxy. So the mass of the 400 billion stars in our galaxy is already pulling this material towards itself. That's why they have no structure as you might otherwise expect. They are streaming towards, the material is being drawn towards our galaxy. You've got to think about that. There were some questions about gravity and what it is. It's an amazing force. If it can drag, this is across interstellar space, if it can drag whole galaxies to join up with another. In the Large Magellanic Cloud, there is another nebula. It's called the Tarantula, and I'm hoping that if you take an axis through that image there, that you can roughly get a spider's 8 legs out of it. Convinced? Good on you. That's what I like to hear. So this is the Tarantula Nebula in the Large Magellanic Cloud. You thought, and I thought, the Orion Nebula was big. This one is huge. This one is huge. If this nebula was where the Orion Nebula is, at night time you could read a book from its light. Once again, there are much better pictures of this nebula, and we can't quite see it that well in our telescopes, but you can certainly discern that spider legs bending up and back. There is a general understanding that the universe is uniform, and on a large enough scale, it probably is. I haven't been all the way out, so I'm not 100% sure. But certainly, and Professor Blair alluded to this insofar as some of the things of the work that he does, you can't do it in the context of a mere solar system or even a mere galaxy. You've got to look at things on a much, much bigger scale. So we are able to look at this group of galaxies. This is, here's the scale here. This distance is 1 million light years. 1 million light year is 9.5 trillion kilometres. So 9.5 trillion kilometres. You can see this little dot here is our Milky Way, and you can see the Magellanic Clouds down towards 7 or 8 o'clock. In our local group of galaxies, there are 3 main ones, 3 big ones: the Milky Way, the Triangulum, and the Andromeda. The Andromeda is bigger than us, and even though the universe, the fabric of the universe, is expanding and dragging all the mass in it away from each other, the gravitational attraction between this galaxy and our galaxy are such that these two galaxies are actually coming together. Over a distance of 9.5 trillion kilometres, gravity is pulling these together. And as you can see around the outside, we've got lots of dwarf galaxies, small ones. And they are arranged in a not uniform manner, so to speak. If we then look at the next scale out, so we're looking at, right in the centre here is our local galactic group. All of these other groups are not stars, they are galaxies. And this is just within, where's the scale? The scale here is 110 million light years. So the next closest group of galaxies to our local group is this one here, the Sculptor. And once again, on a very good clear night, no moon, at Perth Observatory, when the Sculptor galaxy is visible, we can show it to you through a telescope. It's a spectacular view, partly because from our perspective it is edge on to us. We don't see it as a nice big spiral. It's a thin strip of stars that fills the eyepiece. It takes a little bit of time for your eyes to see this image develop. You need to be fully dark adapted, but I promise you, if you get to see it, it is spectacular. That's a long way up there, isn't it? If our rocket hasn't run out of fuel by now, then I'm pretty close to running out of talking about it. This is a logarithmic diagram of the universe. Starting from planet Earth here, you can see the moon, you can see a few things in the atmosphere right down close, you can see the sun, you can see the planets, and then on a logarithmic scale you can see all of these other galaxies right out to the edge of the observable universe. And ladies and gentlemen, that's as far as I can take you in this rocket. The universe may well go on long beyond that, but in terms of the observable universe, that's as far as we can go. I thank you for your time and attention.